Hello and welcome. So in this example, we're going to look at this sinusoidal voltage that they gave us here, and they gave it to us in peak volts to a resistive load. Here. That's just one single resistor, and we want to find the RMS current, average current, peak to peak current, and instantaneous current at the positive peak. Okay? So they gave us peak voltage, and so we can easily find peak current using Ohm's law. So we can just apply Ohm's law and say Ohm's law allows us to put voltage, current, and resistance in play. And if we know voltage and resistance, then we can find the current. So we'll say that current is equal to our voltage divided by our resistance. Specifically, we have our voltage source, which is a peak voltage. That means we're going to be able to get IP using VP and the only resistor in the circuit. And if there are more resistors, we want to use the total resistance, right? So that is the total resistance for this circuit. So we can plug that in and say that our IP value is actually equal to 28.3 peak volts VP divided by our 2,600 ohm resistor, right? Watch out for the kilo ohms on these ones. Set that equal here, calculate it out. We can say that we have 28.3 divided by 2,600, and that gives us that milliamp value. We'll put that in here as one of our final answers here for our IP. Our IP equals 10 point, around that 8 up to a 9 milliamps peak. So we can work through each one of these here. We'll now know that this is our peak amperage here, and we can use that for our I average and our RMS average. We know what those two are, so let's get rid of our ohms down here. We'll say that our RMS average is whatever our peak is, IP, multiplied by 0.707. And that 0.707 is derived in the back of the book if you want more information about that. We know that the average is going to be something similar. It's going to be our IP multiplied by our 2 over pi. And again, that one is also derived in the back of the book if you want more information on that. We also know one more. We know that our peak to peak is equal to our IP multiplied by 2. Right? That's going to be the peak to peak, the full sinusoidal rotation of our full current on our AC waveform. So we'll see that those two peaks can add up together, and we expect both of them to be equal, so it's 2 times the original peak voltage. We could do the instantaneous voltage as well, but we'll do that one after we finish up all of these ones, because that one's a little bit different, but shows kind of the same thing. So let's start with our RMS, and we'll put that into our calculator here. Say that we have 10.9 milliamps. We'll leave that milliamps off for now. And we will multiply that by 0.707. That gives us a milliamp value of 7.7 milliamps RMS. Right? We multiply by a milliamp, we end up with a milliamp. Especially if the other number is just at base, right? 0.707 doesn't have any engineering notation after it. Okay, we'll send that one out, and we'll do the same thing for the next one. We'll say that we have 10.9 multiplied by 2 over pi. Okay, that's 6.93. 6.94 milliamps AVG. That's our average. We do still expect our average current to line up slightly underneath our average RMS value, right? Because our RMS is kind of an average, but it's taking it a little bit faster. It's guessing a little bit more at the value that it offers, right? And so that's going to change its output just a little bit. So the peak to peak current, we can do that one also real quick. We can say that we have 10.9 multiplied by 2. That's going to give us 21.8 milliamps, 1.8 MA, peak to peak. So watch out for each of your endings there. So this last one here is the instantaneous current at the positive peak. We know that relates back to our polar and rectangular forms, and so we can say that that would be considered our imaginary number or our JB term, and we can run it from there and say that that means that our instantaneous current is equal to the I sine of theta. right? But what is theta, right? So theta is given by the at the positive peak here. At the positive peak, we know what that is. So let's look at our unit circle here. Here we see that at the positive peak, we would end up at the 90-degree mark. That's the full rise. And then at that point, we would start to fall again. And then we would go after the negative side of our waveform and then rise up to the zero line again, where we rotate again and we do the same rotation. So we expect the positive peak to be at 90 degrees. And so we know what that value is, and we can plug that in for that. Say that we have IP. Oh, we know what IP is. We can plug that one in too. We can say that that is 10.9 milliamps peak sine multiplied by the sine of our 90 degrees. Make sure your calculator is in degrees for this. Anytime we're using sine, cosine, all that kind of stuff needs to be in degrees. So 10.2 or 10.9 milliamps multiplied by the sine of 90 degrees. 10.9 milliamps is our answer output for that. So our instantaneous current, our I, is equal to 10.9 milliamps. That's our peak current. That's what we expected, right? But if you wanted to find the current at any other angle degree, so a little bit before the peak or a little bit after the peak, you can update this and still get that current out. Determine the instantaneous current at any other location. Right? Let us know if you have any other questions.